Grade 12s, we're going to start our new unit in sinusoidal functions. Yay! And I'm going to keep it short today, just get you started. I have the first sheet in your handouts, if you printed those off, has a series of definitions. It would not hurt for you to go over these. I will use these words fairly regularly while we're talking about these things, so it would be nice if you had them written down somewhere. Would also be nice if you printed off those handouts. It can help you fill things out. So our first activity together is I'm going to walk through the sine curve with you and get you and your friend to work on the cos curve. So we just want to be able to establish what the curve y equals sine x looks like, so that then tomorrow when I start throwing numbers into it and we change the look of it, we'll know what we're looking for. So the first thing I'm going to do is get out my special angles sheet with those special ratios or a calculator, because we're actually going to determine these as decimals this time so I can graph it a little bit more smoothly. So if my curve is y equals sine x, you will remember on your special angle sheet that the sine of 0 is 0. So we're going to have a point 0, 0. I'm going to spread my graph out fairly largely. I'm going to have a value of a y value of 0 here, a y value of 1 here, and negative 1 here, so that I can see this really clearly. Sine of 30 degrees is one that we have on our special angle as well. But since I want to know these as a decimal so I can graph it a little bit better, I am going to be putting decimal 5 instead of 1/2. Sine of 45 degrees is another special angle, but I'm going to write, instead of that root 2 business, I'm going to write decimal 707. Sine of 60 degrees was root 3 over 2, but decimal 866 will be nice for graphing. Sine of 90 is that strange thing that we had on our special angle sheet where it's a 1. Now we're going to start to see some of the same numbers again, because we know with angles of rotation, if we go past 90, sine is still positive, and we see some of the same ratios. Sine of 135 is also root 2, or decimal 707. Sine of 150, again, 0.5, lots of familiar things. Be careful, we're skipping a few in here. We'll have to be careful when we graph it. Sine of 180 is 0. Sine of 225 is also decimal 707, but it is negative. Oops. Sine of 270 degrees is negative 1. And sine of 360 degrees is also 0. So we just have to be careful with some of those gaps, but we're going to draw those on our graph. So 30 degrees, I have a value of 0.5. For 45 degrees, which is right in the middle of these two dashes, I have decimal 707, so about there. 60 degrees is one a little bit further, decimal 866, so closer to there. And sine of 90 is 1. So there is going to be my maximum value, because I know my values turn around and I see the same numbers over again. 0.866, decimal 707, 0.5. Oops, I missed one, didn't I? 0.5 is here. And a 0 at 180. At 225 degrees, I have negative decimal 707. And at the 270, I have my minimum value, the smallest that it goes to, because it's back up to 0 again at 360. So we have a nice, smooth, sinusoidal curve. Oh man, you're going to do a nicer, smoother job because you don't have a lumpy smartboard. But this should be a nice, smooth curve in there where we have a maximum and minimum value. The distance from the middle, we call that middle the axis. And it's the middle of our wave. The distance from the axis to the minimum, or the distance from the axis to the maximum, is called our amplitude. The amplitude for this curve is 1. From 0, the lowest is -1 and the highest is 1. So our amplitude has a distance of 1. Amplitude, help if I could spell, equals 1. So our maximum value is +1. Our minimum value is -1. We also see that it does this smooth curve. It should be smoother on yours than mine. And it would keep repeating that as we had bigger and bigger angles. We would just keep seeing that curve happen over and over again. So the length of time that it takes to do one cycle is called a period. Time for one cycle is called the period. And the period of y equals sine x is 360 degrees. It takes 360 degrees to go from the middle to the top, to the middle, to the bottom, and back to the middle again. That takes a distance of 360 degrees. Our domain, unless I tell you otherwise, that curve is going to go on and on forever and ever. So my domain is going to be x, is a real number. It could be anything. But the y values have a lowest and a highest. So my range, y can be a real number, doesn't have to be a whole number, but -1 is the lowest it can be, and 1 is the highest it can be. And we're going to work on getting that form correct. The x-intercepts for this thing is where we hit zeros on the x-line. I see zeros for my x-intercept at 0, at 180 degrees, and at 360 degrees. And it would keep going forever and ever. My y-intercept is at 0, 0. We've already talked about maximum, minimum, amplitude, period. The intervals of increase and decrease. A little less important and hard to write down, but you can see this is increasing to here, and then we decrease, and then we increase again. We won't write that out formally. These are called sinusoidal functions because we have the word sine or cos. So anything that has sine or cos in it is sinusoidal. It means that it is a periodic function, and a periodic function is just anything that repeats exactly over and over again, but it's a periodic function that is a smooth curve. So we're going to ask you to do this very same process to have our plane regular y equals cos x. So you've got a sample of it in your notes. So you should have this on the handouts that you printed off. You need to fill out the table of values and graph this and determine those key features. A lot of them are going to be the same as y equals sine x, but a couple key things are going to be different. So I need you to do that with your friend. And then you've got some questions to work on page 24 and 25, I believe numbers 1 to 8, but check the website on that.